Hi, everybody. Welcome to the Gaussian Splats Town Hall Part 2, hosted by the Metaverse Standards Forum. I'm Patrick Cozy, a founder of Cesium and Chief Platform Officer at Bentley Systems, and I'm co-hosting this along with Alexei Medvedev from Meta, as well as the chair of the 3D Formats group at Khronos. All right, so let's jump right in. So first, I just wanted to say a few words on the Metaverse Standards Forum. We're a forum combined of over 2,600 organizations, large companies, small companies, as well as SDOs, helping on both pre-standardization efforts, so explorations like what we're talking about today, as well as post-standardization efforts around trying to fill gaps, might be test cases, sample data, documentation, that kind of thing. There are both free and paid options to join the forum. Please check us out there at metaverse-standards.org. Okay, as for considering open standards, we think timing is really important, right? In that if we're too late, an ecosystem starts to fragment and we have all this different software from different vendors and it doesn't always talk to each other, and that's bad for everybody. But then if we're too early, we can stifle innovation where we need the flexibility for things to change. So we're kind of looking for this sweet spot where maybe there's some similarities among approaches that then could be considered for an open standard so that we don't fragment the ecosystem while we're still allow some innovation. So with respect to Gaussian splats, we think we're at this maybe critical moment in time. Okay, maybe there should be some considerations around open standards. And that's what we're here to talk about today. We had a first part of this town hall about a month ago, and it was absolutely amazing. I mean, we had 16 different organizations that's shown here, I think 19 total presenters who joined us with about 450 participants. In what other field on like 3 weeks notice can you rally the world like that? Like super cool. And I think it shows that we're onto something here. And then today in part 2, we have a smaller number of participants. I think I'm seeing about 72 right now. And I think that's good. I think there's still a ton of momentum. And now we have a smaller, more focused group that's going to go a level deeper and really look for some similarities. So we're pretty pumped on that today. Some of the takeaways from last time was this: hey, we want to stay flexible. We want to leverage existing standards and solve something that needs to be solved, right? And not kind of try to boil the ocean and solve everything. And then there's a lot of excitement around what Niantic is doing with SPZ and the potential for that to fit into GLTF, and then for that to fit into 3D tiles. So we'll see more of that today. We've asked each presenter to kind of reiterate some of their use cases and the why of Gaussian splats. We've asked them to show us some of their end-to-end pipeline and where they will fit in there, from capture, content creation, to processing, to visualization and interactivity. Then anything they can share, around any performance, robustness, visual quality trade-offs. So with that said, the agenda, Alexei and I are just kicking things off for a few minutes. Then we're going to go over to Niantic. We got about 25 minutes for both presentation and Q&A. Then we'll go to Bentley and Cesium. And then Meta will be the final presenter. We'll save a few minutes at the end for our global wrap-up and Q&A. Okay, as for the Q&A, I mean, this is all about discussion and conversation. There is a Discord link. We're getting it in the chat there, so please join us there. For any discussion here on Zoom, we'd ask that, if you drop anything in chat, we'll try to move it to Discord so that we have that, as an archive for future interaction. And then Alexei will help MC all of the Q&A with the presenters. Again, Q&A after each presentation, and then at the end. So before we go over to Niantic, Alexei, anything you want to add for today?
You said pretty well, and yeah, I really want to just welcome everyone to this event. I'm really happy that happens. So we have the traction and we have the actual deep knowledge sharing regarding this matter. That's amazing. So let's start.
Thanks, Alexei. All right, so first up, we have Azad from Niantic. And when you kick things off, we always love to know about the people as well. So please give a short personal introduction as well. Over to you, Azad. Not sure if we're having an issue there. So maybe just to keep pace, we could come back and we could just jump to Cesium and Bentley to keep things moving. Is everyone okay with that? All right, so then we'll go over to Jason and Renaud.
Okay, so hi, so I'm Renaud from the iTwin Capture team at Bentley Systems. So last time Jason and I talked about our work on Gaussian Splats and why we need standards. As Patrick very nicely just explained. Maybe we just forgot to mention at some point that Cesium is now a Bentley company, or maybe a better wording would be required here. But okay, we were the same team, just for you to understand why we are speaking together. So as you know, Gaussian Splat, they are a new way to capture reality. They have many advantages compared to traditional photogrammetry, let's say. So today I will remind you how important Gaussian Splats are for the infrastructure. I will show you that they can be used for geospatial applications, both in terms of accuracy and of streaming. And then I will go. I will hand over to Jason because he will go into the details of the formats and 3D tiles. So Bentley is the infrastructure engineering software company, and we don't imagine a digital twin of an infrastructure without any reality capture. So I've shown you last time some GS-based capture results displayed with Cesium GS. Let me show you that again for those who did not attend the previous meeting. So here you have a substation, another substation being analyzed by machine learning, a bridge, a telecom tower, another telecom tower, and the construction site. It was and some details of this construction site that have been acquired. By the way, it's the Microsoft campus. So I hope it gives you a flavor of what we call an infrastructure here. Okay, so traditionally, photogrammetry captures meshes. And here you have on the left side of my slide, telecom tower captured as a mesh. And on the right-hand side, the same telecom tower captured from the same photo photo from a drone, and this is what you obtain with the Gaussian Splats. So it just tells you why we're interested in Gaussian Splats. It's not just that they're more realistic. It gives you something which is very nice to look at, but and to some extent, and for some use cases, meshes and traditional photogrammetry cannot even be used. You cannot work on what you can see on the left hand side of my slide. Maybe this slide could explain you in a better way what Gaussian splats are. I mean, it's a big picture. Here you have a schema when you have at one extreme, if you can see my pointer, something which is called light fields, and light fields is something which is very well known for display and graphics, but capturing reality, light fields are not very commonly used. So here the idea that at each point in space, each point in space can emit light, and this light can be different in every direction. So it's in a way it's very the maximum freedom you can have in a 3D model. And capturing light fields from photos is very, very difficult. Of course, it had some nice application in movies, like in Matrix Reloaded. You can see this image. It's kind of it uses light fields at some point here, but usually it's a lot. It's too much. Too freedom to capture what a light field could be from photos. And what we did most of the time was to go to the other extreme of the schema and using meshes, because on a mesh, on the contrary, each point which emits light has to be to lie on a surface. So no more freedom on where you lie. I mean, you can have the of course the shape of the mesh, but you have to be on a mesh, on a surface. And then each point on this mesh is usually emitting the same light in every direction, at least for the meshes which come from photogrammetry, of course. This is exactly the, let's say, the other extreme compared to light fields. And this is tractable. And we were, of course, able to capture this kind of meshes from photos for the last decades. And then we have that. We have the neural radiance fields, NeRF, and Gaussian Splats, which are in a way in the middle of that, because, for instance, for Gaussian Splats, the points are emitting light. They cannot be anywhere. It's just a set of points. It's just the whole space, like with light fields, and they are able to emit different lights in every direction. But this is encoded in a function which relies on spherical harmonics. So in a way, it's a bit more constrained than light fields, but less than meshes in space and in lights too. So just to make you understand that where we are today, Gaussian Splats are tractable. They wouldn't have been tractable from the at the time we did meshes, because actually the idea behind Gaussian Splats is more than 100 years old, but it has been tractable for just the last 2 years, and that's very nice. So we are here. It might happen that we at some point have something different from Gaussian Splats. Who knows? But today, this is the best compromise, and we really need to have that as a way to reconstruct reality. Last time, let me spend a bit of time on this slide. Last time, some of the attendees were a bit surprised that we were able to be georeferenced and accurate. And of course, for infrastructure, it's very important to be georeferenced and to be able to take measurements. So here's I show you just 3 different screenshots of iTwin Capture Modeler, our solution at Bentley, and this is just a way to show you that we can have the position of one point, clicking on a model which is made of Gaussian Splats. So you have this position in any given geographic system. You can take and measure distances, of course. And by the way, for this particular model with a mesh, we wouldn't even have the cables here, so we would have had no distances, no here in this case. So, but anyway, so you can click on and intersect array with a Gaussian splat. That's the point behind everything here, of course. So you can measure positions, you can measure distances, you can measure areas, whatever you were using, you were doing with your meshes previously. So we are georeference. We are accurate enough for all these use cases. And maybe something which was a bit I mean, not obvious for everyone, is that to do that, we have to do something which is called self-calibration. So self-calibration is something which is a bit tricky. It's a way to start from images, like we have here on the right part of my slide, and know the position of all the cameras and also the position of what you are looking at. So in a way, if you think a bit about that from a mathematical point of view, it's a chicken and egg problem, because to know where the camera are, you have to know the position of the points you are observing in the world. But to know the position of the points you are observing in the world, you have to know where the cameras are. So it took time for the researchers in this domain to design something which they call self-calibration. It's they have very strong theoretical results about that. They know what we can do with it. They know what what they cannot do with it, but it's the way it works. And every, of course, photogrammetry solution or Gaussian Splats solution relies on that for the first part of what you do when you take images. You take these images and you calibrate them, but it's kind of a self-calibration, that's the correct name. But it allows you to have this georeferencement and all the accuracy you need for what I've just shown on the previous slide. Of course, you take pictures. you turn this picture into a nice model, but you have to share it because otherwise it's completely useless. So you have to display, to share, and to stream. This is all about what we are talking here in this meeting. And to do that, the classical solution is to use 3D tiles, and Jason will go into the details about that. But let me show you as an example of how huge a 3D model could be. Let me show you this nice 3D model from one of our users, Nearmap. It's a mesh, right? Let me be sure to tell you it's a mesh, but we want to do that with Gaussian Splats, and it's going to be doable, of course. So imagine the size of this 3D tile model, how huge it is. So it's not just a building, a city, it's a complete region. So let's do the same with Gaussian Splats. And of course, to do that, we need a tiler, which turns the 3D model into this 3D tile set. And of course, each kind of 3D model has to be tiled in a different way. With Cesium Ion, you have different kind of tilers, from the meshes to the design model. And here with the Gaussian Splat, we are somewhere in between. We are in between how to tile a point cloud and how to tile a mesh, a texture mesh. So we are just in between, and we are working hard on that, and we hope we will soon be able to share that with you. And at the end of what I wanted to show you today, and I will hand over to Jason, and he will go into the details of the formats.
Thanks, Renaud. And Jason, we have about 10 minutes left for the presentation before we go to Q&A. Over to you, Jason.
All right. Hi, everyone. I'm Jason Sobotka. I'm with Cesium. I'm on the tiler squad. We work with the incoming data and how it gets turned into 3D tiles. And today I'm going to talk about Gaussian splatting and our approach to handling it within GLTF and more recently SPZ. So a bit of history with our work on this. Last year, we published a draft extension for GLTF, which was very simply just some vertex attributes. And it was a simple approach that we really just wanted to get out there and get a conversation started and see how it fit in our pipeline and what the wider open standards community thought of it. But it was compatible with MeshOpt and mesh quantization, so it had some advantages with the existing GLTF facilities. And it was presented at SIGGRAPH last year, and that's my colleague Adam Morris presenting it there. And there's an open issue still on GitHub, and there's a link down there with the QR code. Feel free to read it and comment, and we welcome all sorts of feedback. So as a high level view of sort of the formats we're talking about, at the highest level, we have our 3D tiles, which is our hierarchical 3D bounding volumes, which contain all the content we want to render. And then within that, we have our GLTF, which can be mesh, point cloud, or as we want to in the future, Gaussian splats, and how that data is represented. Very simply, it can be uncompressed, or you have mesh quantization, MeshOpt compression, and as we hope in the near future, SPZ. So why the switch to SPZ when we already had MeshOpt? After the last town hall, we saw what Niantic was doing and where they saw it going. It really caught our attention. And they're getting impressive results with their quantization techniques, and it's open source. The MIT license is very attractive, and they have actual users, which is always a very positive thing. It's out there, it's being used, it's real. So from that perspective, it's very strong. And the way they handle spherical harmonic data and how it's compressed is very impressive, and was a big open question we had in terms of how are we going to put it into a GLTF in a performant manner that's, both size-wise and decompressing it. So since that last town hall, we've put together a proof of concept that basically looks like this, where we have 3D tiles with GLTF, and inside that GLTF, we have an SPZ buffer. It's just the SPZ buffer as they compress it. And then at runtime, we unpack it and convert it into vertex attributes in our GLTF for position, scale, rotation, color, and opacity. which then can be rendered in Cesium.js using our existing Gaussian splatting pipeline. And again, there's a link down there with the QR code. It's open source. You can go look at it now, and there's a sandcastle demo demonstrating loading an asset that's been compressed with SPZ inside GLTF and 3D tiles. So the results we see are very good, and is really the strongest argument for SPZ. On the left is a PSNR graph. Our baseline was 45 dB, and SPZ and very high level meshopt both meet that. However, the meshopt file is over 30% larger than the SPZ file. So there's a huge savings, and you're getting virtually the same image quality perception wise. And as far as our pipeline goes, whether it's meshopt or meshopt or SPZ, our end user pipeline doesn't really change. They're going to upload their ply data. We're going to tile it in a 3D tile with GLTF, and then it can be rendered in Cesium.js or one of our other runtimes in the future. And this is just a quick video showing just kind of how we're using this data. So this is that substation that Renaud showed, and just kind of the scale we're working with here, where we have these assets on an actual global scale. So going forward, our work is really focusing on integration with iTwin Capture on the Bentley side. We want to take assets from iTwin Capture, bring them into Ion, tile them, and have them ready to be streamed and rendered in our runtime platforms. Improving tiling and rendering performance. We always want to be faster, but also LOD is a big factor in the quality of what we're putting out there, and it's a big focus for us in how we actually handle assets that either didn't have any LOD to begin with, or how we're going to start generating assets with LOD and splats. And then finally, in parallel with all this work is going to be continued open standards work. Any draft extensions we publish out there will be going on as well. So that's my presentation. I appreciate the time, and with that, I open up to questions.
All right, thank you, Jason. Thank you, Renaud. Thank you for being on time, and look, great job just showing, end-to-end pipeline here, and very cool, right? We had the town hall a little over a month ago. You saw the opportunity for SPZ. You said, hey, let's explore that. Then you're able to show, some initial results here. That's what we're trying to do. That's why we're doing these town halls. So we have about up to 10 minutes for Q&A before we go back to Niantic. Alexi is the master of emceeing the Q&A, so please drop any questions in the Discord. If you haven't gotten the Discord yet, you can drop them into the chat here. Then Alexi will help those get answered. So fire away.
Yeah, we still have no questions. Oh, actually, we have first one. And what is the relationship between the 3D.js accuracy and input image resolutions?
That's a bad question for me. Yep, it's a hard question, but it's exactly the same question we have for the usual photogrammetry, meaning that, okay, let's assume that, correct question would be, it depends on how the photograph has been taken, the photos. Yeah, of course. If you take two parallel photos, you have no accuracy at all. If you take two photos that intersect themselves with two nice different angles, you can be more accurate. So that would explain that a correct scientific answer would be it depends, but that's not an answer for the users and for the one who really wants to use that. So usually what we say that if you have the size of your pixel, let's say each pixel is something like 1 centimeter, for instance, 1 centimeter per pixel, we usually say that the accuracy is something like 3 times that, well, 3 times less, meaning that you have 3 centimeters accuracy. That for the meshes. And I don't expect the Gaussian splat to be a bit different because these Gaussian splats have their position in space, the center of each Gaussian, as accurate as what we do with meshes. That's short answer. I don't know if I could complete that to complete my answer. Of course, each Gaussian has a shape, which is like an ellipsoid. It's not a surface anymore, but it really then depends on the kind of Gaussian you are training. Some Gaussians are very thin and placed like a surface. Some other are more like blobs, and here it really depends on what you are focusing on. What is for sure is that if you want to click on a point on your screen and intersect the ray with your 3D Gaussian splat model, it's as accurate as we are with meshes. This is why we can measure distances, areas, etc. So we are not worried about that. Usually what happened with photogrammetry is that you lose accuracy when your first step, the self-calibration, is bad. And this is a different story. And it all goes to how you acquire your images with a drone or whatever. But it's a different story, nothing to do with Gaussian splat.
Thanks. There is one more question. How do you manage rendering frame rate for large scenes with explosion of 3D GIS data? And why using spatial tiles can help viewing from far still expose very large amount of data? How do you solve that?
You want to answer, Jason?
Sure. Yeah, I mean, that's really the problem we're trying to solve. If you treat it like a point cloud and you just try to remove points or use, it makes it easier to render, but you lose detail, and splatting becomes almost incomprehensible if you remove too many points because they are so interdependent for the rendering process. So that's really an active part of what we're trying to solve is not just, there's plenty of algorithms out there that can take the raw photogrammetry, train it into an LOD data set. But a lot of times we're going to be dealing with end user data that has not gone through those algorithms. And so it's just a flat data set. Can we and how do we take that and bring more LODs into it?
Yeah, I think if I could complete your answer, there's no such explosion of 3D Gaussian splat data if you have a correct tiling and level of details tree. The only difficulty here, and related to the question just after the one we are mentioning here, how to handle multi-resolution in the tiling streaming, is the hard question. How do we generate the level of details for Gaussian splats? So it's not like we do with point clouds usually, removing some point cloud to get some points in the point cloud to get less points. It's not like we do with meshes, turning a mesh into a mesh with less triangles and a different texture. It's something in between, but I do not see any reason to generate something with a very few Gaussian to account for your model seen from a very far point of view. But this is more difficult to train and to generate. That was the point with my last slide when I said we are in between point clouds and meshes. So we have to do something which is different, but we will not have something which has too many Gaussian at the same time to be displayed. That's for sure.
So the next question was, I think it's pretty much similar to previous one. How to handle multi-resolution 3GS in the tiling streaming?
Yeah, I think I've answered the two questions at once,
Okay.
because they are really related.
Great.
So for a given resolution, if you need something which is coarser and seen from a further point of view, you have to train again your Gaussian splat or to generate a smaller number of Gaussians from the Gaussians you have, and it's something which is new. Well, nothing to do with what we do with meshes, for instance.
Okay, there is one more question. On one of the slides that was mentioned open standards extension, and the question is, what is timeline for the open standards data extensions, and will a beta version be widely available? So I
Who
see.
takes it?
In terms of SPZ, it's still very early. So I don't know. I don't have a specific timeline or whether what beta would be available for that just yet.
But Jason, everything that you're doing is out in open source and is on GitHub. Is that right?
Correct. Yes. The links that are up, those are out there, and you can download them and run them right now.
And could you even just drop those in chat so people could take a look? Then Alexi, I would say we do one more question here, and then we'll go over to Azad, and then we'll keep the Q&A rolling in Discord to get all the questions answered.
Yeah, and we have a Q&A session at the end, so please hold
Correct.
your question, and then we can return back. So let's do the, I don't know, it's a really short one. Do you expect a SPZ registration as a media type?
Yeah, it was my question. So right now we have, of course, model types that are 3D objects, but there are also now point clouds in the model registration. So I believe SPZ could be a really, or in general, this should be really part of the model media type and not texture media or image media types. So for me, Gaussian splats are really a volume media and like meshes or other. So, and the question is, did anybody look into a model registration for SPZ or any other Gaussian splatting format? No. So that the official media types are from the INA registration. So these are the model types where GLTF and others are registered.
I think it's probably more general question, so not related to the actual presentation.
No, it's more in general. Yeah.
Yeah,
sorry.
we need to return back this in the end of Q&A session.
Okay.
I think, yeah, Patrick, we should go with it.
Yeah, but just quickly, I'm not aware of any of this being registered yet. But yeah, let's come back after the next two presentations. Look, one more round of applause for Jason and Renaud. Great presentation, really moving the needle over the last 5 or 6 weeks, and awesome to see all the engagement. And I think we've teed up Azad just perfectly, senior product manager there at Niantic. They've done a lot of awesome work with the open source SPZ, and then building that community around Scaniverse. So looking forward to hearing the latest. Over to you.
Hello, everyone. Thank you so much for having me here at the Metaverse Standards Forum. I greatly enjoyed watching the previous session and was honored to be invited to talk about SPZ and some of the work that Niantic's doing in the Gaussian splatting world and just radiance fields in general. So yeah, I'm the senior product manager for AR/VR scanning apps at Niantic. I have close to a decade of experience in AR and VR, specifically in the 3D reality capture space. Previously, for the last 5 years, I've been working on a game called Puzzling Places, which is a 3D photogrammetry scanning, which is a game made with photogrammetry scans from around the world, where you put together jigsaw puzzles of those scans. It's very fun. It's a very cool way of experiencing 3D scans in VR. And that led me to work on Gaussian splatting here at Niantic. And I'll talk a bit more about what that entails. I'd like to begin with the idea that capturing the world around us has been super important for people for a very long time, especially photographers, including in 3D. So, for example, let's take this photographer, Johannes Kirkjan, who was an Armenian photographer from the 19th century who went to the ancient capital of Armenia called Ani, which is currently in the eastern border of Turkey, to capture the ruins, basically the newly excavated site, which the city had been basically abandoned since the 1600s. So he captured these sites in Ani in the 1880s. as a way of basically providing virtual tourism for his audience back in Europe. And so I just want to take a brief look at his work. The stereo cards were produced and sold in a box set, and viewers back home would have one of these stereoscopes, and you kind of put the stereo card in there. I'm sure many of us are aware, if not also own one of these old school stereoscopes. Of course, this was very inspiring to me, and being also Armenian and being interested in cultural heritage, especially sites that are like not very well preserved or in active falling apart, or even in being destroyed. This led my wife and I to go and visit the site in 2022, and to basically use the 3D photography tools of our time, which at the time was photogrammetry. And so I went to these sites and captured them in 3D, and with as much detail as I can, using DSLRs, using drones, and of course by keeping the raw data and their poses. As technology progressed with radiance fields, we get to be able to reconstruct these sites with Gaussian splats, which of course make the sites much more immersive, give you view dependent effects, all the things that photogrammetry is not very good at, and of course you can also visit these sites in VR, which has been a key interest of mine. What's also interesting by capturing places in 3D is that you can also, you have full control over cameras. So here, I wanted to briefly show the difference between the past and the present. These are 150 years apart, and you can quickly switch back and forth and see like all the wall has fallen apart, the various details have changed, but the core church on the cliffside there has remained the same, and it seems like it's been in ruin from way before 1880s. But yeah, there's been quite a bit more destruction. Here's another example as well. This is the Holy Savior's Church. It fell apart quite a bit in the 1960s, I believe, due to an earthquake. And currently, it is a UNESCO heritage site, so there is some reconstruction work being done on it. But yeah, this is a personal project of mine, and kind of something that I'm actively working on. So I'm publishing the photogrammetry on Sketchfab, and I'm publishing the Gaussian splats on SuperSplat, as well as Gracia AI, which is a VR playback platform for Gaussian splats. So these are really fun to visit. So take a look. This is very much a work in progress, so I only have a few sites available, but there's more to come. This leads me to Scaniverse. This is the Niantic scanning platform, which has been quite popular because it's free, it's local, and it's also it provides you with a lot of the tools to get started, which is something that I've been asked how to hit. Like, people see my work and they want to get involved with scanning, and they're like, how do I do this? And I wish I had this back then, so I could encourage people to get into scanning and now Gaussian splatting with something as simple as being able to capture on your phone and to process locally on your phone. So I think open standards and open source tooling is like super important for the industry, just because it like opens up the access for people that want to be involved. So Scaniverse is very unique because you can capture and process both photogrammetry and Gaussian splats locally on a phone. Like, this is there might be, I don't know if there's any other solutions that really do the processing locally. The neat thing about that is it does not require, uploading the data to a server for a company to continually pay for a server. You can just have it all locally, and it stays private on your phone. Nothing's being sent up to the cloud, unless of course you'd like to share your scans or your splats to the Niantic map. And on the Niantic map, it's basically a huge global world. It's a 1.5 million splats populating the globe, user splats. And this is also in combination with the splats from the Scaniverse app, as well as splats from other Niantic products like Pokemon Go and Ingress. So there's a mechanic in Pokemon where users can scan their Pokestops, basically uploading a video, and then we on our end can combine quite a few users, data sets and create a combined merged waste splat. These are also accessible, and you can view them in Scaniverse and into the Scaniverse, which I'll speak about shortly. But the neat thing here is you can, once you capture something and process it locally, you can export the PLY and the SPZ splat from your phone directly. So basically, it's a great camera tool. It's a great 3D camera tool that you can use to get started in this kind of nascent industry. Some interesting use cases have come about also besides the ones I mentioned. I mean, again, it's a great way for people to get started, but we're also seeing some uptake in people doing insurance claims, capturing their possessions, and having a more 3D, 3D, and kind of being an interesting way of showcasing. Their whatever the insurance claims are, but also citizen journalism. And there's a project I want to talk about, which is Noni de la Peña, a Peabody award-winning journalist and VR filmmaker. Recently, she set out to go capture the LA wildfires destruction, basically the ones that, what just happened about a month ago. Her students and herself went to about 80 locations. They captured 80 objects, scanned 20 larger areas, basically to reveal the immense damage caused by the wildfires, preserving what they can do for the community, and basically capturing the history, like this moment in time, especially from a ground level human perspective. These are people's homes, these are people's livelihoods, and so the idea is to capture it and to preserve this moment in time and to do journalism. Also these splats were uploaded to the map, so they're actually accessible and viewable by anyone around the world. What's interesting is because we have this global database of splats, we actually built something called Into the Scaniverse. This is a VR viewing app where you can visit all these splats from around the world. All the Scaniverse splats are available, and a number of the merge splats are available, and with more being added every day. We have over 50,000 Gaussian splats to visit. It's kind of like a Google Earth VR, but made with user-generated content. And since launch in December, we've had a cumulative 100,000 users that have checked it out, and a number of them have also uploaded their own splats after seeing it in VR. And so my favorite part about all this is that it's the fastest way of scanning something to looking at it in VR. And again, that's something that a question that I've been asked a lot as a professional is hey, how can I first part is how do I scan something, and the second part is how do I look at it in VR? And that second part, there's ways of doing it, of course, but the simplest way has always kind of been I don't know, make it your own Unity build, which is not a great answer. But thankfully, Into the Scaniverse provides probably the most accessible way of doing it, both because you can capture for free on your phone, but also viewing it on a Quest, which is, of course, the biggest VR platform. So we've optimized our scanning pipeline so that every splat that you produce on your phone is automatically optimized to run into the Scaniverse and in VR. And we're also continually working on increasing the quality of that and kind of pushing the boundaries of what can be rendered in VR. One of the key technologies here is SPZ that makes this all possible, which is, if you're out and about scanning things and you want to upload it to the cloud, you don't want to max out your data cap limit, right? You want to upload something as simple as an image. So SPZ here is a key factor in being able to both upload the data from people's phones, but also more importantly in VR, you want to be able to very quickly jump into a world and out of a world, into a splat and out of a splat, because you want to fly around and explore these things. So SPZ makes that step really super fast, be able to jump in, take a peek into this spot, take a peek into that spot. So that brings me to SPZ. This is kind of one of the latest initiatives from Niantic. Again, this was built for Scaniverse, but the realizing that this could be very useful for the industry as a whole basically drove it so that it can be open source. So it is a way of compressing splats, and also there's quite a bit of detail that's included in PLI files that that gets either compressed or removed, but with a very minimal image loss. I wouldn't say or I can't definitively say if it's exactly one-to-one fidelity, but I think, as the previous speakers spoke about, the results are quite compelling. So I think this is an important step that we would like to see the industry try to adopt. We're realizing that there is quite a bit of adoption already. Here's a few examples: Babylon, Godzilla Pro, StorySplat. Because there's clearly a need to be able to compress these, hundreds of megabyte files into something as little as 10 megabytes, to be able to embed these things in a web page, to be able to download and upload them from your phone. Anything that speeds up the process, I think, is a huge advantage to the industry. So we're really proud to see kind of the uptake here. And we are starting to work more on SPZ. There's some internal developments that we've done that we haven't yet pushed live yet, but it is an open source project. So the GitHub, is linked here, and we'd love to see people send pull requests our way, and discussions and what can be done, what can be improved about the format. A key takeaway here is that we think that Gaussian splats unlock quite a lot of value already today. There's discussions about are things going to get better? Are things going to improve? And of course they will. I can't, as there's been so much innovation in the reality capture space just in the last 5 years, with Nerf's introduction in 2020 and Gaussian splatting today. But I think Gaussian splatting is kind of a big milestone, because it is bringing the world of radiance fields into the world of real time. But I think we can try to combine some of the advantages of meshes, especially for things like physics, for raycasting, for even just having a nav mesh to be able to walk on, with the visual advantages of Gaussian splatting. So those are the things that we're exploring. We're looking at even things like LODs, which was spoken about. I don't think we have much to say on that end, but again, these are areas of interest for us that are being worked on. Things also, better performance optimizations like the skyboxes. Why do those need to be splats themselves? They can probably be compressed into a texture. That's also how they work into the Scaniverse. That leads to really good, much better performance optimization. Also, GPS coordinates, that would be nice to be included in these Gaussian splats so that they can be georeferenced. We would love to see SPZ as part of a subformat in GLTF and GLB, similar to Draco compression for meshes. It just would, enable uploading and downloading of very simple files like GLTFs to include Gaussian splats. And so I was very happy to see Cesium also pushing on that end to include Gaussian splats in these open formats. I want to just kind of end with saying would love to work together. Please open up discussions, open up issues, or reach out to me directly to talk about these things. I'm going to be working a lot more on SPZ now that Into the Scaniverse is out the door, and we're going to be continually developing that as well. But yeah, this is the right people to talk about SPZ with, clearly, and there's quite a bit of uptake just in the world of Gaussian splatting and 3D reality capture, and we're at the beginning here. I think this is really the start of quite a lot of innovation to come. I think the value is slowly being unlocked. I've been in the world of reality capture for enough time that the same questions come up over and over from various industries. Hey, can you capture this? Can I use it to capture that? And with photogrammetry, the answer was always yes, but you need to be kind of an expert both on the capture side, on the processing side, on the mesh fixing and texture fixing side. So it required quite a lot of skill sets. And thankfully, with Gaussian splatting, I think that it simplified quite a bit of things. All the drawbacks of photogrammetry, all the areas that it was very limited in, now is kind of trivial with Gaussian splitting. I wouldn't say it's like a full one-to-one replacement, of course, as we talked about with some of the limitations, but it's a huge step forward, and I think it lowers the barrier to entry, which photogrammetry had always a lot of trouble with. So any tools that enable both developers and users to be able to capture and create experiences and products with Gaussian splatting is, I think, a big plus. So yeah, thank you all for listening on this talk, and yeah, I'd love to answer any questions.
Azad, amazing talk. We're going to do a round of calls for you. Look, really appreciate everything that you showed there. I thought the historic culture examples really good. What you're doing both on the scanning and VR side, kind of showing full workflow, really exciting. And then the organic adoption of SPZ with all the logos you showed up there, that's super cool, and that's a testament to the work being done. And then also very much appreciate your interest and willingness to work with folks like the GLTF community. So with that said, we have about 7 minutes or so for questions, and I've seen them, they've been flowing in. So Lexi, over to you.
Yeah, so first one. What is very impressive about Scaniverse Gaussian splatting is that it appears to retain the world scale. And is it using LiDAR for small scale and GPS for large scale to preserve scale?
It's actually a bit simpler than that. It's using ARKit on iOS and AR Core on Android to capture the scale of, to retain the scale during capture. So of course, LiDAR enabled phones might have slightly better scaling than a purely, RGB based ARKit instant, but yeah, it's using the tools that are available already. And that is a key part of also being able to view things in VR. It's as soon as there's scale is like, let's say 5% off, you instantly notice it, and something about it is a little bit weird. So having one-to-one scale for viewing spots in VR is like super key. Yeah, so yeah, thankfully ARKit and AR Core does make the having retaining scale quite trivial.
Okay, great. So the next one, for Scaniverse on device splat creation, how long does it to processing? How long does the processing take? Is there a limit to the number of points per splat? Does it use the phone's GPU to do the processing? And is the creation methodology based on existing paper, or is it internal and proprietary? Sorry, it's a bunch of them. That's same person ask.
Yeah. So in terms of points captured and trained, so the interesting thing is we have a tiered kind of checkpoint system when it comes to splatting, and similar to other methods, but it's a way of the first processing step that you do takes about, it depends on how long your capture is, of course, but let's say 30 to 45 seconds, you get a 500,000, 600,000, or sometimes less, of course, if it was a quick capture, 1,000 Gaussians. And then you have another 4 or 5 steps of enhancement that you can enable. So that gives you the ability of like saying, okay, this is not enough detail, process it for longer. And so you can add as many details. I think probably the top end is like 1.5 million Gaussians by the end of it. Of course, it is using the GPU on your phone, and it needs basically all the resources it can get. So you have to, it's not something that you can do in the background. Your phone has to be actively training the splat. So there's a certain limit in a consumer app how long you would want your phone to be inaccessible. So that's a, of course, a limitation, but it's something that it is improving, of course, as GPUs are getting better. On Android, it's a similar situation. The performance is not on par with iOS when it comes to the time it takes for training, but that's also something that we're continually working on to have basically parity between the two. The last question in terms of LODs, I don't think we can speak about that just yet. I also don't know if I know the answer to that. Yeah, if there's anything to talk about in the future, I'm sure we will share it.
Great. So we still have time. So the next question is, does into the Scanniverse support the Apple Vision Pro?
Currently, it's a Quest only experience, and Quest 3 and Quest 3S. Again, purely from a GPU limitation, it's not something that we can open up to like the lower Quest tiers. We are exploring other platforms as well, you know, the PCVR, Pico 4 Ultra, and Apple Vision Pro. But it's not that trivial, especially with Apple Vision Pro having to, you know, kind of remap controller inputs to hand tracking gestures. That's just at the base level, but also just how splats can get rendered. But yeah, it's a WebXR experience. It's built with Niantic's own kind of game engine tool built on the web called Niantic Studio, which is also, by the way, available for free. And you can import splats and build experiences with that. So that's kind of a neat, again, a tool that people can use. I don't know if there was a second part to that question.
No, that's pretty much it. So then I'll combine two different persons' question into single one. They somehow related. Is there any roadmap for SPZ specification document and any plans to add some flexibility, extensibility into SPZ, custom per splat buffers or extra metadata that could be accessible by some shader when SPZ would be embedded into GLTF?
In terms of a roadmap, I don't think there's anything that I can talk about just yet, but I can just say we hear you, and it's something that we're working on. So stay tuned as to like what for more documentation or road mapping, and if you have specific, you know, specific requirements or specific suggestions, definitely open up a discussion point on the GitHub, and we'll be able to address it there. But yeah, this again, it's a new project. We're still kind of like figuring out like we're going to be working with people, and we're ramping that up slowly, but hopefully we'll be able to address people's concerns sooner rather than later.
Maybe
Okay.
one more question, Alexei?
Yes, I'll choose something else then. Can Scanniverse app take data from external camera, LiDAR data inputs?
Currently, the Scanniverse app is purely built around the internal scanning experience. So, you know, it's not something that you can import your own video or image data sets to. Again, it's like very much a big part of it is ARKit. So it's not at the moment Scanniverse is insular in that sense. For that to be opened up, I think a few things would have to change. So at the moment, it's very much a scanning. It's like a, you know, an all-inclusive ecosystem.
All right, excellent Q&A. Let's do one more round of applause for Azad.
Thank you for having me.
Of course. And I think there's still a few more Q&A questions there in chat. So feel free to jump on Discord and answer them. And then again, at the end of the town hall here, we'll do just a broad Q&A. I wanted to share two quick things. One is, I've been watching the number of participants, and I have to say, instead of seeing people dropping off, we're actually seeing people added. So we're holding strong at 94. I think great sign, great engagement. And then you'll see Lawsey's doing a lot of work to bring all the questions into the right place. So I did want to do a big thanks to Lawsey, Jeff, and Lisi, who've done so much coordination work to bring us all here today. So a round of applause for them. Okay, and next up we have Meta, Nemanja, and Ashish. Welcome back, and over to you.
All right. Hello, everyone. Let me go ahead and share. Thanks. Hello, all. This is Ashish, and I'm joined by my colleague Nemanja as well. Nemanja, I see you there probably. Yes. Okay.
Yeah, I'm here.
Okay.
Hello.
All right. Hey. So we'll go through a couple of slides on the state of Gsplat at Meta, and then what are the opportunities we are learning. based upon the current implementation, and then we will close it with a roadmap. Quick introduction. Again, as I said, my name is Ashish Singh. I am product management lead for cloud AI in Reality Labs at Meta. Nemanja, go ahead.
Yeah, and my name is Nemanja. I am the software engineer in the Codec Avatars team, and also working together with Hyperscape closely, the cloud AI.
Awesome. So quick agenda for us. We'll talk about the current state of 3D Gaussian Splat at Meta. We'll go through the pipeline overview. What are some of the lessons we have learned, and what are the opportunities for interoperability? To get us started, today what we have seen for the last few years is a growing interest in representation of 3D realistic environments in consumer enterprise use cases. And the success of these use cases we have seen is determined by the realistic representation of these 3D representations in how accurately and realistic they are represented in these use cases. 3D Gaussian Splat is something we are seeing as an emerging technology, which is bridging the gap and able to fulfill a lot of these use cases that we are seeing. With that in mind, we released an app called Hyperscape app on the Quest for Quest ecosystem last Connect 2024. Basically, if you have a Quest, you can go ahead and download that app, and you can see some of the initial scenes that we are rendering using our cloud edge servers. The idea for this tech demo app is to really understand how that is being used, really understand and get a deeper insights and understanding from our partners on what are the other potential use cases we foresee. And then based upon that, we will continue to evolve the future of 3D Gaussian Splat and realistic representations for Meta and Quest ecosystem. So how did that work? How did we reach the launch of Connect 2024? To discuss in more details, I will hand it over to my colleague Nemanja. Nemanja, go ahead.
Yep, thank you. All right, so I guess first of all, like in the last presentation on this topic, we went briefly over the pipeline and discussed some of the file format considerations. This time, we decided to kind of have a slightly deeper dive on what we're doing in the pipeline itself, because there were a lot of questions around performance and how maybe the data is generated. So to start off, I mainly work on the Gaussian splatting runtime itself, which is the actual component that executes on the edge devices, whether that's on device or in the cloud or somewhere else. And I get the chance to collaborate with different teams, right? For example, for training environments, we have a separate team for that kind of has focused on creating a very, very robust reconstruction pipeline to really handle all these inside out, reconstructions, which are somewhat more challenging than, when you have a certain object in the middle of, then you have to reconstruct it from outside in. And on the other hand, we also have this relatively elaborate codec avatar generation pipeline, which has gone through multiple iterations. And one of the latest ones is to generate these real-time ready avatar assets that are able to be skinned, that we can actually apply LODs on, and we can bring into VR without requiring like PCVR experience or something like that. So we're able to do rendering of avatars on device, as well as we're actually able to render even scenes on device up to some complexity. And we have ways to kind of go from more detail to lower detail, and to be able to scale from device to cloud and back and forth across all these experiences to make sure that the final experience is optimal and you get good frame rate and good experience. And in the end, we find these two representations and two efforts to kind of together form this social experience that we want to kind of showcase. So go to the next slide, please. So what is the point of this unified Gaussian splatting runtime? Like we could have certainly developed this in two separate directions, but we wanted to have a way to actually get a sense of if we can combine multiple different Gaussian splatting representations into one pipeline and be able to render all of them together. What would that entail, and how would this change within our rendering infrastructure? And one of the things we also wanted to do is to allow a lot of different people with different profiles to be able to onboard into real-time rendering, to bring their own expertise and their own ideas about how to optimize Gaussian splatting and how to, work within such a code base. And we kind of achieved this cross-platform with a backend written in Vulkan that is able to go from basically all the platforms that we know of, including like Apple platforms with Vulkan BK. And naturally, as you work within this space, you have to deal with a lot of different representations. Researchers and engineers will bring different things. Eventually, things will settle into something. But we are able to handle loading and basically rendering of data coming from PLYs, from SPZ, from some custom SPZ formats that we'll mention later, as well as like from different kind of PyTorch archives, stuff like that. Anything basically that contains some sort of a representation that someone thought of. There's probably a way to render it within this engine. And what we really want to see as a step forward is to kind of unify some of those things and settle on a representation that will kind of make the things simpler for us on our end as well. If you go to the next slide, we can cover, I think we've been over this slide as well before, but to basically cover the basics of the pipeline is that you want to be able to animate the splats. It gives more life to the scene and gives more like more dynamics and more interesting final experience. We would be able to apply animation both for the avatars and as well for certain parts of the scene, like maybe there's some foliage, moving in the background, stuff like that. So this comes as the first step, and it's definitely optional because if the whole model is static, then we don't have to really do anything about it. Then we have the projection step we are familiar with that kind of takes our 3D representation, whatever that is, can be compressed, uncompressed, some sort of streamed file format, and puts it into a screen representation, which is just 2D splats that we can then sort based on some criteria for what we consider view depth, and then we finally rasterize. And for that, of course, we will leverage hardware rasterization in many different forms, and we try to optimize experience for VR. So that means including stuff like foveation and other kinds of optimizations that we can do along the way. And if we go to the next slide, we'll start with basically, I wanted to also mention a very important step is how you design your culling pipeline, which we've seen also in the presentations before. You have these different kind of tiling systems and melodies and the ways to bring different parts of the representation into your main memory to what you want to render. And here I just briefly mentioned that, for example, for VR, if you want to kind of avoid sorting for both eyes separately, you need to have at least one unique way to represent all the splats. And for that, we do a simple union, for example, of all visible Gaussians across both eyes. That's like a simple trick. And it's very relevant for the environment, right? You definitely have a lot of splats to call, and you should definitely be using some sort of primitive pipeline unless you already kind of remove things with an LOD system. So if you go to the next slide, for the projection step, we experiment with that many different representations. This is like the key stage, and this is where you can get all this efficiency from compressed formats because you can actually process them directly in the shader. And to improve the quality and fidelity of some of the artifacts that we've been seeing when you get close up in VR with Gaussians, I mentioned here this particular paper. This is the optimal projection for 3D Gaussian splatting that kind of helps hide some of these artifacts by not just rendering splats that are parallel to the view plane, but also kind of slightly tilted. And this, of course, requires some more support in the vertex shader. And if you go to the next slide, we come to sorting, which, of course, you really want to make as fast as possible. This is one of the core parts of the algorithm. Of course, you don't have to call it every frame, but the idea is that we use a radix sort that is very well optimized across different types of architectures, and it's based on this one sweep paper that people are probably familiar with. In the next slide, we can basically just give a brief description of how the vertex shader works as well. In the typical hardware rasterization pipeline, you could go, for example, with instance rendering of splats. Each splat will have certain 2D properties that you can expand each canonical unit square to and get some sort of a renderable representation that can be turned into pixels. And in the next slide, we have the fragment shader that basically just evaluates the kernel. And the important part here is that different kernels will give you different properties, different qualities, and this comes from the data. And this is something that we need to kind of embed into the actual file format. You can, of course, change the accumulation. Different orders of rendering the splats will open up different kind of optimizations. So that's also important to explore and consider. And of course, specifically for VR, you can have a foveation pipeline that kind of helps to improve performance, and you don't need to render things in too much detail on the peripheral parts. And if we go to the next slide, I would like to go back to our file format considerations, and we explored the things that are already there. I think they're pretty good, and they can probably be reused into one unified file format that also includes compression. So to start off with, I think it would be really great if we already supported all the PLYs out of the box, because there's a lot of files out there that are still just regular old PLYs that come from the original paper. And that means having some baseline support for cyclic harmonics is probably a worthwhile investment here. So starting off with this GLTF compression, we could probably design some sort of extension system where we're able to handle this in GLTF. So I'm not, just to be clear, I'm not an expert in GLTF itself, but I feel like most of these attributes can be very well mapped to existing vertex buffers. We use accessors part of the specification. And then we probably need some way to extend or account for the fact that cyclic harmonics are a bit more involved. And yes, this will create huge files, which is why we also need compression. So we can, in our current pipelines, we use, as I mentioned, different kinds of representations, and we have a certain metadata file that kind of helps us disambiguate different content. So if you go to the next slide, as I mentioned, training itself has a huge impact on what you can do with the final rendering, at least from our experience. And while this may not be the final representation of the rendering parameters or something like that we want to embed, some sort of metadata needs to exist, and it needs to cover things like, I don't know, for example, are your cyclic harmonics in HDR space or LDR space? How do you blend these? Can you apply something as a post-processing for tone mapping later, etc.? What about sorting, for example? There's at least 3 different criteria. I've seen one in the GLTF extension proposal, and we know that there's the basic one with the view depth, and there's the one with just simple ray distance. So all of these things could come from the training as well. So you want to kind of mimic that in the rendering pipeline as well. And on the other hand, there's also this technology that we have built that is related to continuous LOD. And the idea is to basically organize the splats in a scene such that you can progressively load and render them. And as your load on your system gets bigger, you can kind of cull more splats from the end, reduce the overall amount of splats in the scene, and still get a picture that is kind of plausible. Combining this with foveation, for example, also works wonders. Basically, you can cull different parts of the pipeline, different parts of the model, and still display something that looks neat. And yeah, we could probably go to the next slide. I mean, kernel actually, sorry, go back for a second. One thing I didn't mention is that kernels, have to be specified in some way, right? You can have your typical Gaussian kernel, which is the exponential function or something similar to that. Then you have the quadratic kernels, linear kernels, etc. There are different papers that have experimented with kernel types, and they produce different kinds of results. And using this also to gain extra performance, etc., is a valuable thing to consider. So we can go on to the next one. Right, dynamic content is also very important to us. As I mentioned, dynamics bring a lot of scene and characters to the rendering, to the environment. And we should both be able to have some sort of way to support foliage, which is partial animations in parts of the model, or maybe a separate asset. There should be a way to support keyframe animations. With compression, that could actually be fine. The file shouldn't be too large. You can imagine these things as being some sort of a 3D GIF building block in the future in AR, VR experiences. And then, of course, there's skinned assets. The more we kind of solidify this pipeline and make it close to traditional rasterization and rendering techniques, so basically treating them as meshes, we'll be able to kind of utilize more of the older technologies, including LBS and similar. And the next slide. Right, so compression is kind of a complicated topic. There's a lot of different work out there. Not all of it gets to be super practical, but SPZ is a great file format, and we definitely use it, load it, and we love the memory compression that it gives us. Also makes things a bit more faster to load, faster to send over the network, etc. And we also use a modified version of SPZ, which allows us to have indexed codebooks, texture compression, and other kinds of custom stuff that comes from various papers. It helps us to push compression even further. But of course, this would need to be considered in the future standardization. At least I think a generic way of indexing into a codebook is probably something that can be handled in a standard way. And I am not sure if, for example, all of the attributes and all the compressed components today can be actually handled in GLTF directly, just referring to SPZ, but with some extensions and some work there, I'm sure that a common standard can be defined. And yeah, that's about it. I think that the next slide, Ashish can give you a bit more like information about our upcoming roadmaps and products.
Thanks, Nemanja. Yeah, so as I said, what we have today is an Hyperscape app. There are pre-scanned environments available for viewing. When you get a chance, take a look at it. And we're seeing the growing needs of various use cases. And in really three big buckets, we will be evolving those in coming quarters and years. One is a user-generated scans, obviously starting with creators and influencers, and really giving the community an opportunity to try this technology and really experiment with it. There are some examples of avatars being introduced and bring that co-presence capability in this realistic environments. Think of the ruins example that was given by Azad in the beginning, and you can bring your co-friend and actually watch that. Pretty amazing experience. So we will be working towards combining the realistic experiences with co-presence of your friends or colleague that you want to enjoy together. And the last but not the least is how do we bring animation and dynamism into this realistic environment, which is what the area of exploration is being covered with the last bullet point of dynamic G-splats. So that's where our pretty exciting stuff. Stay tuned, and we'll be bringing more and more excitement into the app and other areas of Quest ecosystem. That's all we had. Thank you. We can take the questions now.
All right, thank you very much. Appreciate it. Ashish and Nemanja, look, really great job going to the next level of detail here. I love the walkthrough of the vertex and fragment shaders and the trade-offs there, and just how you're doing the culling for VR. And it was great to see some similarities across all three presenters today, you know, the references to GLTF and the SPZ. And then you also brought a number of new things to the table around the animation and dynamic splats. So let's do a few minutes of Q&A specifically for this talk, and then we'll open it up to just any topics. Alexei?
Yes. First question. In Meta slides, where the same woman is in three different places in the room, if this is the same model, how do you handle different local lighting?
I see. So these are three separate avatars in terms of like in memory. It's just that I'm using this as a test model, so I was just kind of instantiating it all over the place. As for relighting itself, if I understood the question, that's kind of currently work in progress. There are some promising results, but nothing that we would show yet at this point.
Okay, great. So the next question is, did you compare using fragment shaders versus compute for the rendering part? What were the performance and advantages, downsides of each?
Well, I guess if you're familiar with both of these pipelines, you know that the sorting pipeline in the compute path can be a bit challenging. You need to resize, you need to account for the tiles and so on. So we would rather let the hardware figure that part out, and we sort only the Gaussians themselves. In terms of performance, it depends on the platform. I think that with basically GPUs with huge bandwidth, you can do more interesting things. And on GPUs later on mobile, you have to kind of make every use of the hardware available, including like hardware sterilization.
Do you see the dynamic splats being standardized at the same time as the static splats are standardized? And static splat structure is somewhat stable, but I have seen multiple vastly different ideas about how to do animated splats.
I suppose for this particular question, it depends kind of where we take the standardization. I think that the first version doesn't have to contain dynamic splats necessarily, but it should, at least contain most of the static splat aspects so that we are able to be more flexible about how we can share assets across different systems.
So that's the questions for the sessions.
All right, let's do one more round of applause for Nemanja and Ashish. So we're doing fantastic on time. So really great work from the presenters and also just the questions coming in. But we have maybe 10 minutes or so to wrap up and to do broader questions, across all three presentations. Then, of course, Alexa and I are looking for guidance on how do we continue the conversation? What's the most useful thing that we can do for the ecosystem? What are the similarities that we're seeing? So please keep the Q&A coming in the chat and in Discord.
I see GLTF as similarity pretty much persistently. So that's partially the answer. So there's a couple of questions. Let me parse them first.
And then while you're doing that, I'm just bringing up a screen share for the wrap-up slide here with some links for resources for the Metaverse Standards Forum. And then, Lossie, if you wouldn't mind, would you drop some of these links in the chat as well for where the videos and so on are? Thank you.
Okay, so the first question, I think it's probably broader for everyone, not to be specific for the latest session. So lighting of Gaussians, I've heard anecdotally of people treating the color vertex property of Gaussians as the diffuse color. Is this approach valid? Has there been any attempt to structure Gaussian in PBR-ish way? And that makes it easier to apply traditional lighting approaches during the rendering. And basically, it's a really long question, but that's the sense of this. So how we want to treat the lighting, it should be always outliner for the typical PBR model, or we can fit into this. Again, it's a question for any presenters.
But in a way, the lighting in the 3D.js is already representing the light response of the PBR in various directions. And so it seems a bit taking a step too much. The moving into the color space is done usually only at the beginning of the frame, and it's very specific for the viewpoint at that frame only, and so in a way it also represents the PBR response for that angle.
So the continuation of this question is, so yeah, let's assume if not the above, is there any good progress on including real-time lighting into Gaussians or getting accurate spectral and reflections?
Maybe I can give a couple of lines on that. Basically, I think the diffuse lighting is a bit easier to solve if you just want some sort of image-based real lighting. But speculars are quite difficult because even the Gaussian optimization itself can warp the geometry so that speculars only look good. Speculars look good from most angles, but the actual geometry is not the geometry that you would expect. The depth of these Gaussians is completely off. And this is something that you need to then account in your optimization to be able to change this. But it's not an easy problem for sure.
Okay, so the next question is required vertex attributes. What are the absolute minimum set of attributes for the set of such as positions, rotations, colors, etc., that would create a valid Gaussian splat? And in GLTF, for example, positions are only truly required vertex attribute. Would a splat diverge from this and require additional attributes to minimally function? Or are there reasonable defaults like all colors are white and alpha, blah, blah, that can be used if some of these attributes are not present?
I can take that one. In terms of what's required, you're going to need position, scale, and rotation, and the diffuse color or spherical harmonic zero and the opacity to really get the effect. If you ignored color or opacity, it's just gonna look like a mess. But position and scale and rotation are absolutely required. Otherwise, you just can't do any of the rendering.
Okay, great. So the next one, I think should be a fast one. Are there any GLTI plus KHR Gaussian splitting sample data for testing or even with embedded SPZ? I think it's to Cesium.
The Sandcastle demos we have on the published branches do have sample assets that you can render.
And Jason, could you provide a link for folks?
Yes, I pasted it in chat, but I will paste it again in case it just got scrolled up.
But even a direct link might be helpful.
To an asset or the repository?
Maybe both.
Both. Yeah. Are there standards to quantitatively benchmark the DGS performance? Silence speaks itself, right?
Meaning the training or the display?
Or
the answer will be both.
let's assume both.
Yeah. It's not that easy. I mean, it's just because you can stop the training. Yeah. The number of iteration of the training is something which you can say whatever you want with that. You can stop the training before and say it's faster, but then you have to measure the error you are doing with that. So it makes the research paper about on this question even more difficult to compare. But the good news is that, well, you have the implementation. You can just test yourself. But yeah, well, I mean, another answer would be we often say that Gaussian splats, and it was said for NERF a bit too, are faster than photogrammetry. Well, it really depends how far you train them and how long you wait. At least the more correct answer would be at least the main difference with photogrammetry that you can see them being trained and stop whenever you want, at least when it's not something which is batch on a cloud service or whatever, but you can just stop that. Exactly what we've seen at the beginning of NERF with this very nice implementation by NVIDIA when we could see the NERF being trained live. It made every people think NERF are faster. Well, they are not faster, but you can see the beginning of the training from the beginning and the NERF becoming more and more accurate. We have the same with Gaussian Splats. But as for a benchmark of how fast it goes, it runs, I'm not sure we have that, not yet.
So Alexei, we're coming to the top of the hour. So I'm wondering, maybe I can ask you a question and then we can ask everyone a question, right? In terms of just looking for similarities, looking for next steps. I do think I see a lot of folks, experimenting farther and farther with GLTF and SPZ. And maybe one thing we can do is just compile the links to the SPZ repo, to the GLTF pull request. We share that out. Maybe we do another town hall in like 6 weeks or so. And then we just try to continue as much of the conversation as we can on GitHub. And then, of course, I imagine Khronos 3D formats would be moved out. I mean, what do you think? Are these reasonable next steps?
Yeah, it sounds perfect. Yes, it's definitely, well, a lot of food for us to consume during working group meetings to discuss this. And yeah, I'm kind of really surprised on the good side of this. That's so much attention for this kind of direction. We tried to kind of convince ourselves as 3DF working group to not think about this. But to me, that's like really strong signal that we should take this seriously and keep going. And I think we have ideas how we want to proceed with this. We'll definitely want to keep like this needle moving for sure. Yeah, that sounds amazing. Yes.
And what do you folks think? Any other plus ones or other ideas there? Neil?
Yeah, I was just a big plus one. I think we should absolutely keep the conversation going. And SPZ, I think but like the same the same thread came up on the last town hall that SPZ and GLTF, there seems to be a really good synergy. It would be great to work with a big applause to Niantic and all the fantastic work that they're doing. It would be great to really make sure that we're aligned on making SPZ an open standard, not just open source. And we're delighted at the forum here to foster that discussion, because I think that's an important next step.
That'd be amazing. Other feedback for directions here? Cool. And Evo's noting in chat there the benchmarking ideas. I agree. It's going to be super important so we understand the trade-offs. Alexi, final comments or questions from you?
I just want to say thank you for all our organizers and presenters to make it happen. Just, yeah, that's only positive emotions regarding this. That's amazing. Thank you.
Yeah, for sure. Look, the collaboration here is fantastic, right? I think the field in general is very collaborative. What we're seeing here in Gaussian Splats is even setting a new bar, and it's great to see so many folks keep turning out for these town halls. So I think with that said, maybe we can start to wrap up. And as I said, we'll follow up with the resources for those GitHub repos. This was recorded. We'll share that out. We'll share the slides. But let's do one last round of applause for Lisi, Lalsi, Jeff for organizing this, and then for all of our presenters from Meta, from Niantic, and from Cesium and Bentley.